review briefly, we can induce magnetic fields by passing current through a wire. And so there's two situations. Either the current is flowing out of the page toward us, which is represented by a dot, or into the page away from us, which is represented by a plus sign. And so we use the left-hand rule. If the current is coming out of the page, the magnetic field will be clockwise, this direction. And when the field is into the page, the magnetic field will be counterclockwise, this direction. We can also induce voltages if we have a permanent magnetic field, north and south, and the flux lines from this field directed from the north to the south. If we have a conductor and we force it down through the field, the conductor will have a voltage and possibly a current for a closed loop, but a voltage induced in it, and the voltage polarity will be set up in such a way that the magnetic field induced around the conductor will oppose the permanent field of the permanent magnetic field that the conductor is being passed through. And so what I mean is here on the bottom, the flux induced around the conductor will be in the same direction as the permanent field. And so this will be a counterclockwise. And as you can see, that means that the current or voltage being induced in the conductor will have a polarity directed into the page. Now, if we have a conductor and we force it up through the magnetic field, have a very similar situation. The magnetic field induced around this conductor will be set up in such a way that its magnetic field opposes the magnetic field that is being forced through. And so in this case it will be counterclockwise, like here. And the voltage induced and the current induced will have a polarity that is out of the page. Now consider a DC circuit. So. And the circuit is going to pass through an inductor, and so we're going to look at the cross-sectional image of the inductor here. And so imagine that these are the coils of wire that make up an inductor, and they've been cut in half. And so the DC current being applied, let's say that on the right of the page the current is outward directed, out of the page, and on the left-hand side of the inductor it is into the page. And so every turn that has the current coming out of the page, will have a clockwise magnetic field induced around it, just like we see here. And everywhere where the current is directed into the page, we will have a counterclockwise magnetic field. Like so. So we're passing current through these turns of coil, and we get these magnetic fields induced around each section of the wire that makes up this inductor. Now let's take a look at this a little bit larger. We have two neighboring turns of wire. They're drawn here. And two neighboring turns of wire over here. And the fields here are counterclockwise, and here they are clockwise. Now, as the current, and let's assume that this circuit has a switch in it. When the switch is open, no current flows, but when the switch is closed, the current starts off at 0 and then starts to increase toward some value. As that current is increasing toward its maximum value, these magnetic fields are growing. So at 0 there's no magnetic field at all. And as the current starts to increase, the magnetic flux field around these turns of wire begins to grow. And so for these two neighbors, this wire is inducing a magnetic field that is directed clockwise. As that magnetic field continues to grow, this field line is going to grow and cut the neighbor. And so the field line is above the wire, the field line is directed to the left, and it's passing down across this turn, its neighboring turn in the inductor. And so when this field line cuts this conductor wants to induce a voltage, just like you see here. When the conductor is passed through a magnetic field, it wants to induce a voltage around it. It's the same thing we see here. We see a magnetic field that is cutting past the conductor, and it wants to induce its own magnetic field. And when it does that, the magnetic field induced is going to be in the same direction as the field line that cut it. And you can see that that field line being induced, caused by the cutting of the field line, is opposing the magnetic field that this turn of the wire already had around it. That means that the voltage being induced in the wire from the magnetic field cutting the wire is going to be in the opposite direction. It's trying to induce a voltage that's going into the page. Right? The current's actually flowing out of the page, but the induced voltage from the magnetic field cutting the conductor wants to be directed into the page. And that means that the current is going to be slowed. The current will not rise to its maximum value instantaneously. As the magnetic fields grow, the induced voltages in the wires are opposite of the direction of the voltage actually being applied to the wires, and therefore the current grows more slowly. Now consider that the current in the inductor has reached its maximum value. And so imagine that this part of the conductor had a magnetic field around it that was clockwise. And as the current in the circuit increased, that field grew larger and larger, and eventually that field cut across. As these magnetic fields were growing, because they expand, as they're growing they cut across the conductor. And as those flux lines cut across the inductor, we saw that they induced voltages in the opposite direction that they were actually flowing, and that slowed the current down. Rather, it prevented the current from increasing to its maximum value instantaneously. Now let's say that the switch is closed and the current flowing through the inductor is at its maximum value. The magnetic field has grown to its maximum value. If we reopen the switch and the current can no longer flow, these magnetic fields now want to collapse. They want to go back and collapse back down around the conductor. And when that happens, when this magnetic flux line is collapsing back toward the center of the wire that it's centered around, these flux lines are now cutting the neighbors again. And when they cut the neighbors will induce a voltage, have a voltage induced in them, that is in the same direction as the flux lines here. Right? This flux line is cutting from bottom to top. Flux line around the conductor will be in the same direction as the flux line that's cutting the wire. And you can see that the induced voltage now, when the magnetic field is collapsing, is in the same direction as when the current flows through. So we allowed current to flow through these turns of wire, and we had clockwise flux lines being induced. When those clockwise flux lines grew, they wanted to induce counterclockwise flux around the wires. But when they're collapsing, they want to induce clockwise. They want to keep the current flowing through the wire so that those flux lines can be induced around the wire in the same direction. And so this is a very interesting property of inductors. Remember that an inductor resists the change in current. So when the current started off as 0 and we closed the switch, the current wanted to increase, but the flux lines growing was slowing that change of current. The current could not change instantaneously. When we reopen the switch and the magnetic field lines collapse, the current in the inductor was already at some maximum value. When the flux lines are collapsing, because the switch was opened, they're cutting the neighbors in such a way that the current, being at a maximum value, wants to remain at a maximum value. The collapsing magnetic field lines are trying to keep the current flowing in the inductor. And so it does not matter if the current is trying to increase or if the current is trying to decrease. The inductor is going to try to stop that from happening. It's going to resist that change. The change will take place. but the inductor is resisting it and it's slowing the rate of that change. The inductor is storing energy, and that energy is stored when the switch is closed and the current flows and these flux lines grow. The growing of those flux lines is the stored energy. When the switch is reopened, the inductor has those magnetic fields collapse and is trying to return that energy back to the circuit. So the inductor in that sense is an energy storage device. The amount of energy that the inductor stores is equal to 1/2 the inductance, which is measured in henries, times the current passing through the inductor squared. And so again, when the switch is closed, there's no energy stored in the inductor at first. As the current starts to flow, as the current increases, the amount of energy stored in the inductor is also increasing. And eventually the current will reach some maximum value, and it won't increase anymore. And the maximum amount of energy is being stored in the inductor. When the switch is reopened and the magnetic fields collapse, that energy is being returned back to the circuit. That returned energy to the circuit is trying to keep the current flowing. Now eventually the inductor will run out of energy. As the magnetic field collapses, it's trying to induce a current in the same direction that it was flowing in originally. And as the magnetic field collapses, the current will start to reduce and the inductor will give up its energy. And eventually the magnetic field will collapse completely, the current will stop flowing completely, and there will be no more energy stored in the inductor, at which point there will be no more current passing through the circuit. Now let's consider this circuit, and again this is a bit of review. We covered this in DC circuits. We have a circuit here with a source voltage Vs of 12 volts, and our circuit has a double pole single throw switch, and so the switch can either be in position A or position B. When the switch is flipped into position A, the current being supplied by the source voltage will pass up through the inductor L1, which is 100 millihenries, and up through the resistor R1, which is 1 kilo ohm, and through point A back to the positive. So when we flip the switch into position A, the current starts off as 0. The current starts to flow, and some of that energy is used to induce a magnetic field around the inductor. The magnetic field grows, and so the current doesn't flow at the same rate as it would without the inductor in the circuit, because some of that energy is being given to the inductor to be stored as a magnetic field. Eventually the inductor's magnetic field will grow to some maximum value. No more energy can be stored in the inductor, and the current in the circuit will be its maximum value, whatever V divided by R is. Right, so I max, the maximum amount of current that can flow in the circuit, is just whatever our source voltage is divided by R1. That's the only resistance in the circuit. The inductor does have some resistance, but it'll be small. We'll neglect that for now. If the switch were flipped into position B, right, so we started off with it open, no current was flowing. We flipped it into position A, the current started off small, and some energy was stored in the magnetic field, and eventually the current reached some maximum value. Now the current's flowing in the circuit. We flip the switch into position B now. The magnetic field starts to collapse. When that magnetic field collapses, the energy is given back to the circuit, and it tries to keep the current flowing in the same direction, right, just as we saw before. And so the current continues to flow up through the inductor and through the resistor, through the switch to position B, and we'll get a loop of current over here on the right hand side of the circuit now. Right? There's no more source voltage. The energy that's causing this current to flow was the energy that was stored in the inductor's magnetic field. Eventually, as the magnetic field collapses, the inductor is losing energy, and the amount of current that is flowing in the circuit will decrease, and eventually it will reach a point of 0 amps. And at that point, all of the energy that was stored in the inductor's magnetic field will have been returned to the circuit, and there's no more energy left stored in the inductor. So in this example, the maximum current that can flow in the circuit will be our 12 volts, which is our source voltage, divided by the resistance of the circuit, which is 1 kilo ohm, and we'll get 12 milliamps. That is the amount of current that would flow in the circuit if there was no inductor in the circuit at all, right? If we just had one resistor, one 12 volt source, resistance is 1 kilo ohm, we would expect 12 milliamps to flow. That's going to be the maximum amount of current that can flow in the circuit. But we know that the current starts off at 0 and it's going to gradually rise to this 12 milliamp value. And so if we look at the amount of current flowing in the circuit, and here we'll use a lowercase I because it's not a constant value, that means a changing or an instantaneous current. As time goes on, the switch is open at first, no current flows. We flip the switch into position A, and the current will start to rise up to the maximum possible value, which in our case is 12 milliamps. And we say that the amount of time that it takes for this current to reach the maximum value, the amount of time is equal to 5 time constants, which we use the Greek letter tau to represent time constants. And if you remember, tau is equal to L over R. So the value of L over R, which is tau, is roughly 1/5 of the amount of time it takes for the current to reach its maximum value. And so in my example, tau is equal to L over R. L in my example is 100 millihenries. R is 1 kilo ohm. It's going to take 100 microseconds. One time constant, tau, is equal to 100 microseconds. So the time it takes for the current to rise all the way up to the maximum value of 12 milliamps is equal to 5 times tau. So the time is 5 times tau, which is 100 microseconds. The time it takes for the current to rise from 0 up to 12 milliamps will be 500 microseconds. And so if we were to look at this curve, roughly, after one time constant, we have some value of current, not 12 milliamps. After 200 microseconds, right from 0 to here is 200 microseconds, the amount of current in the circuit will rise even more, still not quite to 12 milliamps though. After 3 time constants, we're even closer. After 4 time constants, we're very close. And after 5 time constants, we are essentially at 12 milliamps. Not quite, but very close. Close enough for us to consider 5 time constants to be the amount of time that it takes for the current to reach the maximum value. And so we saw a formula, again, last semester in DC circuits. That says that the instantaneous current flowing in the circuit is equal to Vs over R, which is the maximum amount of current that can flow, times 1 minus E, which is Euler's number, to the negative RT over L power. This formula tells us the instantaneous current value at any point in time t for a circuit that has a source voltage, a single resistance, or a total resistance, and again, total resistance and inductance. And we can determine what the instantaneous current is at any point in time. So we've already determined that a single time constant, tau, is equal to 100 microseconds. Right, so each interval of time here represents 100 microseconds, 500 microseconds total. If we wanted to know what the current was after one time constant, or 100 microseconds, or at any point in time, right, 150, 175, 380 microseconds, any value of time along this curve, we can determine the instantaneous current using this formula. So let's find out what is the value of the current after 100 microseconds at this point in time. So again, we'll use this formula, and this is a review of DC circuits. The instantaneous current will be Vs over R, which is the maximum current. I already know that that's 12 milliamps, times 1 minus E, which is Euler's number, to the negative R, which is 1 kilo ohm, times T, which is the point in time that we're looking for the instantaneous current. In this example, I want to know the current at 100 microseconds, divided by the inductance, which is 100 millihenries. And so to solve for the instantaneous current, we will start by evaluating the exponent of E. Right, So let's figure out what the exponent of E is first. It's going to be 1 minus E to this power. And so if we look at a calculator, it's negative 1 kilo ohm, which is 1,000, times 100 microseconds, 100 EE to the negative 6, divided by 100 millihenries, so 100 EE to the negative third. And so the exponent here reduces down or evaluates to be negative 1. And if you remember from DC circuits, it's not a coincidence that this worked out to be 1, or negative 1 in this case. The exponent always works out to be the number of time constants that we're looking for. The amount of time that we've let pass in this example was 1 time constant. That's what the exponent evaluated out to be. If we had plugged in 200 microseconds, we would have gotten negative 2. 300 microseconds, we would have gotten negative 3. If we plugged in 475 microseconds, we would have got negative 4.75. Right, that's 4 3/4 of the total amount of time that it takes for the current to increase. So no coincidence that that worked out to be negative 1. Now that we've worked out the exponent, we will take e to that power. And so depending on your calculator, you probably have an e to the x button. And so I have to hit second and then my natural logarithm button. And I get e to some power. I want that power to be negative 1. E to the negative 1 power. So I get I is equal to 12 milliamps times 1 minus, and e to the negative 1 power is, and I'm going to write this as a decimal rather than engineering notation, I got 367 milli, so I'm going to write that as 0.36, and I'll round that to 8. 0.368. And so now we will subtract. So we're going to take 1 minus 0.368, and we get the instantaneous current is equal to 12 milliamps times 0.632. 0.632. And this is a number that we see in the book as well. The book will tell us that after 1 time constant, we will have risen to 63.2% of the total maximum possible current that can flow in the circuit. That's exactly what we're seeing here. You see that the maximum is 12 milliamps. We're multiplying by 0.632, which is the same thing as 63.2%. And so we're saying that after 100 microseconds has passed, the current is going to be 63.2% of the maximum value of 12 milliamps. And so 12 milliamps times 0.632 is going to be 7.584 milliamps. The instantaneous current at this point in time is 7.584 milliamps. And so that's the value of the current here. My graph's not perfectly to scale, but the current here is representative of 7.584 milliamps. Now let's assume that the switch is still in position A. It's been in position A for a long enough amount of time that the current has risen all the way up to 12 milliamps. And we've left the switch closed. The current is at 12 milliamps now. Now we flip the switch into position B. And what we're going to see is that the current in the circuit will reduce back down to 0, and again, but not instantaneously. It will take some amount of time for that to happen, and it's the same amount of time. It'll be 5 time constants. And so again, tau was determined by the resistance and the inductance, and so from the point in time that we switched the switch into position B, it will take 1, 2, 3, 4, 5 roughly time constants for the current to reduce all the way back down to 0 milliamps. And so in this example, let's say, well, what is the current going to be 250 microseconds after we flip the switch into position B? And so if you remember, this formula is for rising currents. Those are rising currents in an inductive circuit. And for falling currents, we'll say that the instantaneous current is still Vs over R, but this time it's just times e to the negative RT over L power, right, without the 1 minus. So this will be for falling currents. This is when the magnetic field is collapsing. And so I'll go ahead and work this out again. The instantaneous current will be equal to Vs over Vr, which is our maximum possible current. Right, Vs over R is 12 milliamps. times E to the negative R, which is 1 kilo ohm, times T, which I'm looking for 250 milliseconds, microseconds, divided by the inductance of, and I'm going to go ahead and erase this, the inductance of 100 millihenries, divided by 100 millihenries. Okay, and we'll work this out the same way that we did before. Start by evaluating the exponent of E. All of this is the exponent. So the instantaneous current will be equal to 12 milliamps times E to the negative, and we'll go ahead and work this out. We have 1 kilo ohm, which is 1,000. Well, actually it would be negative 1,000, right? It's negative. Negative 1,000 times 250 micro, so 250 EE, negative 6, divided by 100 millihenries, 100 EE to the negative 3. And so, again, no coincidence that this worked out to be negative 2.5, because 250 microseconds is 2.5 time constants, right? Each time constant is 100 microseconds, and so 250 is 2.5. So again, the exponent worked out to be the number of time constants that has passed, negative 2.5 time constants. So now we'll find e to the negative 2.5 power, e to the negative 2.5, which is 82 milli. So the instantaneous current will be equal to 12 milliamps times, and I'll write this as a decimal rather than in engineering notation. It's going to be 0.0821. And so what this says is that after 250 microseconds, the amount of current that is flowing in the circuit is only about 8%. Only about 8% of the maximum value, right? So if 12 milliamps is 100%, after 250 microseconds, we're only at about 8% of that current value. And so the instantaneous current will be 12 milliamps times 0.0821. And actually, let me do that a little bit differently. Let's say 12 e to the negative 3, right? 12 milliamps times 0.0821, so as not to confuse you. That would be 985.2 microamps. 985.2 microamps. And so after only 2.5 time constants, the current in the circuit has already significantly reduced, well over 90%, and it will continue to reduce as time goes on. And you can see that the rise in current is very rapid at first, and then it starts to slow down, right? The slope of the curve here is very high, whereas the slope of the curve here is almost flat. Same thing when the switch is flipped into position B, the slope here is very steep, and then as time goes on, the slope is almost flat. And so we see very little change in current here as time goes on. We see the most change in current here within the first time constant or two. Now let's consider what might happen if we have an inductor in an AC circuit. And so for now, there's only an inductor in the circuit, there's no resistors. And I'm not even really interested yet in what the voltage value or the inductance value is. We just want to look at the characteristics of what happens when that inductor is in an AC circuit. And so first let's recall that in the DC circuit, the voltage, and I'll do the voltage in blue, the voltage started off at 0. When we closed the switch, the voltage rised instantly, and then we were at some maximum value. In the last example, it was 12 volts, whatever value it happens to be. But what we saw with the current is that when the switch closed and the voltage rose instantly, the current rose gradually up to some maximum value, right? And so the green line here represents the amount of current, and the blue line here represents the change in voltage. And then if we were to reopen the switch so that the voltage dropped back down to 0 as time went on, what we saw with the current is that the current fell like this, right? Very rapidly at first, and then a little more slowly as time went on. Now, this is what happened in a DC circuit. For an AC circuit, however, the voltage is not constant, right? There's no switch that opens and closes. The voltage in the DC circuit was either 0 or maximum. In an AC circuit, however, we're going to see something that looks more like a sine wave, where the voltage never instantly changes from 0 up to maximum. It's changing slowly, and this is because of the rotating coil in the magnetic field. And sometimes the voltage is negative, right, so that the polarity has changed. So sometimes it's positive and minus, and sometimes it's minus and positive polarity. Now let's start by looking at the point in time when the voltage is at a maximum. The sine wave, of course, continues on, right? It will repeat itself forever, as long as we continue to rotate the coil in the magnetic field. Let's start by looking at what happens when the voltage is at a maximum. When the voltage is at a maximum, the current in the circuit wants to start to rise, and it's going to rise sort of like this logarithmic curve here. Except the voltage is not a constant, right? As soon as the current starts to rise, the voltage is already starting to fall. And so the current is flowing, it's flowing, it's flowing, and the voltage starts to fall, fall, fall. When the value of the voltage falls below the voltage, the maximum voltage that was stored across the inductor, the magnetic field starts to collapse. And when that magnetic field starts to collapse, it's giving its energy back to the circuit, and it's trying to keep that current flowing. And so even though the voltage reaches a 0 point, there's still energy in the circuit being consumed. The energy was stored in the inductor. Now it's being given back to the circuit. And so the inductor is trying to keep the amount of current flowing in the circuit. So again, even though the voltage has fallen all the way to 0, the amount of current in the circuit has still risen all the way up to that point in time. Okay? And now that the voltage starts to go negative, the inductor is starting to lose its energy. It's losing energy, it's losing energy. And let me try to draw this a little better. As the voltage starts to drop to a negative, the current in the circuit is going to start to reduce. What we're seeing here is essentially this, right? The current is reducing. The inductor is giving up its magnetic field, the energy stored in the magnetic field, and it's running out of energy. Eventually, the inductor loses all of its energy. And what happens now is, now that the voltage is at a maximum in the opposite direction, the inductor starts to grow a magnetic field, but in the opposite polarity. And so now that the current is flowing back in the opposite direction, because the current is going in the negative direction now, where before we may have had all of the current into the page on the left of the inductor and out of the page on the right, that's now switched. Now the current's coming out on the left and going in on the right. So remember, we looked at cross-sectional diagrams of the inductor, and we said that on one side current maybe was coming out, and on the other side it was maybe going into the page. And so now we've switched polarities. The voltage is in the opposite direction, and the current is starting to flow the opposite direction through the inductor. The inductor's given up all its energy. It tried to keep the current flowing in that same direction, the original direction it was flowing, right, in the positive direction, let's say, whichever direction that represents. And now the inductor's given up all of its energy. The voltage is being applied in the opposite direction, and now the current starts to flow the opposite way. And so now the inductor is starting to build up a magnetic field in the other direction, right? All of the polarities have changed. Current's flowing in the opposite direction. North and south poles have switched. Polarities of voltages have changed. Everything's changed, opposite direction. And so the inductor starts to store its magnetic field, this time in the opposite direction. The current is flowing in the opposite direction through the circuit. It's growing its magnetic field. It's storing energy. And again, at the point when the voltage reduces back to 0, the inductor has stored as much energy as it could, and then it starts to give that energy back. And it tries to keep the current flowing the opposite way through the circuit, right? And by opposite, I mean not forward direction, but reverse direction, right? So remember, the polarity of the voltage is constantly switching. Sometimes current wants to flow clockwise through the circuit, sometimes it wants to flow counterclockwise. And so what we see here is a pattern of two sine waves, essentially. And this will continue on forever. And they are 90 degrees out of phase. So for one complete sine wave, that is 360 degrees. Let's say that this is 360 degrees. Here in the middle of the blue sine wave, this is 180 degrees. And here at the peak, that is 90 degrees. And here at the minimum, that would be 270 degrees. And so what you see is that the voltage was rising, but the current didn't start rising until 90 degrees later. And as the voltage started to reduce, it was at 0 at 180 degrees. Well, that's when the current was at a maximum. And the voltage continued to decrease until it was at a minimum at 270 degrees. That's when the current was at 0. The voltage started increasing again toward the 0 point, and it reached 0 at 360 degrees. That was when the current was at a minimum. And by minimum, I mean maximum, but flowing in the opposite direction. And so we see two sine waves here, and they're out of phase by 90 degrees. And so this is what happens when we have an inductor in the circuit. And consider this, which one leads, the voltage or the current? If you started at 0 point in time and you went through time, which waveform rose first? The voltage rose first, right? The voltage rose first, and then the inductor, the current through the inductor rose sometime later. And so we have a little saying, we call this Eli. Eli says that in an inductive circuit, which is what the L stands for, the voltage will rise first, and then the current will rise second, right? The voltage comes before the current in an inductive circuit. So we call that Eli. We're going to see in a later chapter that we have ice, which is going to say that in a capacitive circuit, the current actually comes first, and then the voltage comes later. And so we'll see that in a later chapter. But the way that you remember this is Eli the Iceman. Eli the Iceman. That says that in an inductive circuit, again, the voltage comes first, and the current comes later. And we'll see in a later chapter that in a capacitive circuit, the current comes first, and then the voltage comes later. E is another symbol for voltage, the electromotive force. And so we've not added any resistor to the circuit yet. Right? This is for a purely inductive circuit. Only inductors in the circuit, no resistors. If we only have an inductor in the circuit, the voltage and the current are 90 degrees out of phase. So from the peak of the voltage to the peak of the current waveform is 90 degrees out of phase. And so if we imagine this as vectors, imagine we have a voltage vector. Well, maybe I'll do that in blue for you. Try to be consistent with my colors. Blue is the voltage vector. Right? And the length of the vector represents whatever the voltage value is, the peak value, possibly the RMS value, depending on what we're looking at. But the length of the arrow represents the maximum value. And the vector is actually a phasor, which means that it rotates. It's going to rotate counterclockwise. And so this represents the coil rotating in the magnetic field. When the coil is perpendicular to the magnetic fields, we get maximum voltage. When it's parallel to the magnetic fields, we get minimum voltage. Right? And so this arrow is a vector that is rotating. We call that a phasor. And it's rotating. That represents the rotating coil in the magnetic field. Now, the voltage comes first. It's rotating. It's going counterclockwise. And it is leading the current. And so the current is a vector that is 90 degrees behind. And so as these two are rotating, we have the voltage and the current, and they are rotating, and the voltage is leading the current, right? The longer blue vector, which is the voltage, is leading the current vector. And it's leading by 90 degrees. And that will be the case as long as the circuit is purely inductive. There's no resistor in the circuit. Now when we consider our vectors for voltage and current, we're really only interested in the phase angle as the relationship between the two vectors. So what I mean by that is the voltage, we're always going to consider this voltage to be at 0 degrees. Right? And now I don't mean absolute zero, as in on the positive x-axis. I mean that as a reference point, the voltage is at 0 degrees, and the current is at some angle behind it. It's always going to be 90 degrees behind. And so the current, we will say that the current in the circuit is going to be at an angle of negative 90 degrees. The current is 90 degrees behind the voltage. Right? And so again, I don't mean that the current is always pointing straight down. It's rotating. What I mean is that the angle of the current is 90 degrees behind the angle of the voltage. Right, so we're talking about the phase difference, the difference between the two angles, not their actual absolute values of their angles and which direction they're pointing. The angles they point is constantly changing. These vectors are rotating constantly, right? They keep going counterclockwise, and they don't stop, assuming that we have a complete circuit and we're applying power to that circuit. So again, by the phase angle, I mean that the current is 90 degrees behind the voltage. Okay, let's add some numbers to our circuit. Now let's say that we have a voltage, and I'll do the voltage in blue, and the voltage is a sine wave, and again that's representing the rotating vector, the coil rotating in the magnetic field. And so let's say that we have a maximum voltage of 14.14 volts, and the minimum is negative 14.14 volts. And so those are the peak values. Anytime we do calculations in an AC circuit, we really want to be using the RMS values. And so remember that VRMS, the RMS value, which means that this is the equivalent DC voltage that produces the same power in the circuit. And so since the power is the same, that's the value that we're interested in, right? We want to be able to compare this to something simpler like a DC circuit. RMS values allow us to do that. The RMS value is equal to 0.707 times the peak value, right? And so the peak value here is 14.4. So our RMS voltage is going to be 0.707 times the peak value of 14.14 volts. I chose these numbers on purpose, 14.14 volts, because that means the RMS value will be 10 volts. So we're going to say that our voltage over here is 10 volts. Now remember, our voltage is a vector. It has direction. And we don't mean the absolute direction of the vector. We mean the relative direction. And we're going to use the voltage as our starting point. Everything is compared to the voltage. Our voltage is almost always going to be at 0 degrees. So we need to represent the voltage as a vector, 10 volts at an angle of 0 degrees. And let's say that the current in this circuit, and I'm just going to make up a value, let's say that the current in this circuit is 10 milliamps. Now the current is a vector as well. And so remember that the voltage is our reference at 0 degrees, and that the current in a circuit that only has an inductor is always going to be behind by 90 degrees. And so our angle for the current in an inductive circuit will be negative 90 degrees. Now we know that Ohm's law says that the resistance is equal to the voltage divided by the current. And so the voltage in our circuit is 10 volts at an angle of 0 degrees, and the current in the circuit is 10 milliamps at an angle of negative 90 degrees. And so what is the resistance of this circuit? And so the resistance of the circuit is going to be 10 volts divided by 10 milliamps. So remember the rules for dividing vectors. We divide the magnitudes only. So 10 volts divided by 10 milliamps is going to be 1 kilo ohm. I didn't use green here for any particular reason. It's going to be 1 kilo ohm. And when we divide vectors, we subtract the angles. So 0 minus a negative 90. Right? The angle is going to be 0 degrees minus a negative 90 degrees. And so when we subtract a negative, we add positives. The resistance of the circuit is going to be 1 kilo ohm at an angle of positive 90 degrees. And the inductor doesn't actually offer resistance, right? Resistors offer resistance. Inductors resist the change in current. And so to call this the resistance is not actually an accurate term. We actually call this the impedance, right? So we're not going to call this resistance, we're going to call this impedance, and we label that with a Z instead of an R. The impedance of the AC circuit, of this particular circuit, must be 1 kilo ohm at 90 degrees. And we figured that out just by using Ohm's law. So in this example, we said that the impedance was going to be 1 kilo ohm at an angle of 90 degrees. And it's no coincidence, really, that the impedance was at a positive 90 degrees, because Ohm's law says that R is V over I. V is always at 0 degrees, or almost always at 0 degrees, and the current in a purely inductive circuit is always at negative 90 degrees. It always lags by 90 degrees, right? So the voltage is leading the current by 90 degrees. The current is 90 degrees behind. And anytime we divide these, and we subtract 0 minus negative 90, we're always going to get positive 90. And so that means that the impedance of a purely inductive circuit, no resistor in the circuit, the impedance of a purely inductive circuit is always going to be at positive 90 degrees. We can take that at face value. It will always be that way. As long as there's only inductors in the circuit, the impedance of the circuit will be at positive 90. And we don't have to do any other calculations. We just know that it will be at positive 90 degrees. Let's look at one more DC circuit here. And I've not labeled the voltage. I've not labeled the value of the inductance. Inductance is measured in henries. Let's think just for a second about how does the inductance affect the circuit. Remember, the inductance is the property of the circuit that resists a change in current. And so we have a switch in our circuit. This is time, this is voltage. At first the switch is open, there's no voltage. And then all of a sudden we close the switch, the voltage instantly rises, and now we have some high voltage, right? If the inductance is small, the inductor resists the change in current. If the inductance is small, the current, and let me do this in green, the current changes very quickly. Right? That would be an example of a small inductance. Now, compare that to what happens if the inductance is large. And again, inductances resist the change in current. If the inductance was a large value, you'd see something more like this. Okay, so what does that mean? The inductance is resisting the change in current. If the inductance is small, it doesn't resist the change in current very well, and the current rises very rapidly. It only takes a short amount of time for the current to rise. If the inductance is large, and again the inductance is resisting the change in current, it's going to take a very long amount of time for the current to rise to its maximum value, right? So this would be the example of a large inductance. I'll just write large L. This would be an example of a small inductance, small L. So the inductance is directly responsible for the amount of time it takes for the current to rise and also to fall if we were to reopen the switch after it had been closed. Now consider the size of the inductance in an AC circuit. So with an AC circuit, as time goes on, the voltage is a sine wave. And how is the current going to react if we have a small inductance? Let's say small inductance, small L. The voltage is a sine wave. If the inductance is small, the current is going to rise rapidly, and it's going to fall rapidly. Okay? And so we're going to see that the current changes very quickly, that the current has time to rise up to its maximum value. What would happen though if we had a large inductance? Well, when the inductance is large, the current needs more time to rise. And so if the voltage again is a sine wave, and we have a large inductance in the circuit, the current only rises a little bit. It takes a long time for the current to change. So when the inductance is small, the current rises very rapidly. When the inductance is small in an AC circuit, the current rises relatively rapidly. And when the inductance is large, it takes a long time for the current to rise, right? After a significant amount of time, we only saw a small rise in the current here. In an AC circuit, we're only going to see a very small rise in the current. And so the inductance, though it's not resistance, it's a opposition to change in current, right? Whereas resistance is an opposition just to current. The inductance sort of offers this resistance to the circuit. When the inductance is small, the current has enough time to rise to a maximum value because the inductor is not doing a very good job of resisting that change in current. If the inductance is large, though, that's sort of like having a larger resistor in the circuit. because the current needs more time to rise. And so there's not very much time for the current to rise. And so the maximum and minimum values of the current is not very large. So let me summarize that. If we have a large inductance in an AC circuit, that means that the current, I, will be small. And why is that? Well, because the current does not change very rapidly when the inductance is large. It takes more time for the current to rise up to a large value. And so the current does not have the amount of time it needs to rise to that large value. So large inductance means smaller currents. And again, small inductance means that I will be larger. Okay? So again, the inductance is not resistance. It's opposition to change in current. But it sort of has a property about it that does affect the current, right? Large inductances will lead to smaller currents. Smaller inductances will lead to larger currents. And so this is what we mean when we say impedance. The inductor does not offer resistance per se, rather it offers impedance. So it still affects the current, but not in the exact same way that a resistor does. Now consider one more situation here. We have an AC circuit with an inductor. The AC voltage is being generated from a coil rotating in a magnetic field, and that coil can either turn slowly or it can turn very rapidly. So what I mean is if the coil is rotating slowly, we might get a sine wave that looks like this, right? This represents the voltage with time, right? And so that means that there's a large period. It takes a long time for the coil to make one complete rotation because it's turning slowly. Now on the other hand, if the coil is turning rapidly, more quickly, you might see something like this. Okay? And so that means that it takes less amount of time to get one complete rotation out of the coil if the coil is rotating more quickly. Right? And so these are direct representations of frequency. Right? This is a low frequency. Low frequency means a long period. Low frequency means that the coil is turning slowly. This is a high frequency. High frequency meaning a shorter period, less amount of time. Less amount of time to complete one complete rotation, and the coil is rotating within the magnetic field more rapidly. And so let's think again about, well, how does that affect the current? Remember that when the inductance is large, the current rises slowly, and when the inductance is small, the current rises more quickly. Regardless of whether the inductor is large or small, though, the current does not rise instantaneously. It takes time. And so that's what we're talking about here, is the amount of time. And so let's say that we have inductance. When the voltage is switched, the inductance rises gradually, right? So this is time. This is the amount of current that is flowing, or instantaneous current, maybe I should say. Instantaneous current. And so it takes time for the current to rise. Well, in a low frequency, the current has a nice long period of time to rise and fall. In a higher frequency, the current does not have as much time to rise and fall. And so what that means is that when the frequency is low, we're giving the current plenty of time to rise up to some maximum value. When the frequency, though, is high, there's only a little bit of time for the current to rise. And so less time means less current. So with low frequency circuits, the current will be relatively higher, and with a high frequency circuit, the current will be lower. So we saw how the inductance itself affects current. Now we're seeing how the frequency affects current. And so for a large frequency, we're going to have higher currents. I'm sorry, I wrote large here, I meant low. Right? With a low frequency, we're going to have higher currents because it has more time to rise, right? More time to rise up to a higher value. With a higher frequency, we're going to have lower currents. Lower currents. So there's two things that are affecting the value of the current here: the inductance itself and the frequency. Large inductance means small current. High frequency means smaller current. Smaller inductance means larger current, and lower frequency also means higher current. So these are the two factors that are going to affect the currents in our circuit. So let me re-summarize that. If the inductance is a big value, then the current will be a smaller value. They're inversely proportional. If the inductance goes up, the current goes down. If the inductance is a small value, then the current will be a higher value. And again, that means that they're inversely related. If the inductance goes down, the current goes up. Now, if the frequency is a high value, if we have a high frequency, that also leads to lower currents. And if the frequency is a small value, that will lead to higher value currents. And so the frequency and the inductance both are inversely proportional to the current, right? If the inductance goes up, current goes down. If the frequency goes up, the current also goes down. And so the current is inversely proportional to the inductance and the frequency. And so what does that say about the impedance? What does that say about the impedance? Well, if the inductance is small, that means that the impedance must be high, right? Impedance is sort of like resistance, but in an AC circuit dealing with inductors. Sort of like resistance. It's measured in ohms still. And if the current is a high value, that must mean that the impedance is small, right? So just like in a DC circuit, if the resistance was large, the current would be small, and if the resistance was small, the current would be high. And so the impedance is inversely proportional to the inductance, right? A small inductance means high impedance. So if we have a small inductance, that means high impedance. And if we have, not inductance, current. If we have a large current, that means we have a small impedance. Same thing over here. If the current is small, that means the impedance must be high. And if the current is high, that means that the impedance must be low. And so this means that the impedance is directly related to the inductance. More inductance means more impedance. Less inductance means less impedance. We also see that the impedance is directly related to the frequency. A high frequency means a high impedance. A low frequency means a low impedance. And so what that boils down to is that the impedance is going to be proportional, directly proportional to the inductance and the frequency. If the inductance goes up, the impedance goes up. If the frequency goes up, the impedance also goes up. They're directly related. They're proportional. And so when we have a proportion, we can make this be an equation if we have some proportionality constant. Well, it turns out the proportionality constant is 2 pi. And so we can say that the impedance of an inductive circuit is equal to 2 pi, 2 times pi, times the inductance of the circuit times the frequency of the circuit. So why was the proportionality constant 2 pi? Well, that has to do with the period of a sine wave measured in radians, right? So one complete cycle of a sine wave is 2 pi. That's where it comes from. Half of a sine wave, of course, is pi, and 90 degrees is equal to pi over 2, and 270 degrees is 3 pi over 2. Okay, so the 2 pi comes from the sine wave cycle, right? That's one complete oscillation of a sine wave measured out in radians. That's where this 2 pi comes from. We could derive this formula in more detail, but I think it's important that you just know the formula. And so impedance technically means the combination of resistance and what we call reactance. The inductor itself in the circuit only contributes what we call the reactance. So we've only seen circuits with inductor so far. We've not mixed an inductor and a resistor. And so I've been calling this impedance so far. Technically that's true. But when we go to look at circuits that have resistors and inductors, we want to make sure that we know that the inductor offers what we call reactance, right? We call this the reactance. And we denote that by X sub L, where L stands for inductance. We want to say that the inductor reactance is equal to 2 pi times L times F. Now when we go to look at circuits that have inductors and resistors, then we'll be looking at impedance, and we'll need to be combining reactances with resistances, and we'll see how to do that shortly. So let's look at a simple circuit. We have 10 volts at 0 degrees, and unless stated otherwise, this is RMS. Right? This 10 volts means 10 volts RMS, not peak. Okay? 10 volts at 0 degrees. The sine wave is oscillating at 1 kilohertz, and we have an inductor in the circuit that is rated at 10 millihenries. And so, how much current flows in the circuit? How much current will flow in the circuit? Well, we know that the current is equal to the voltage divided by the, let me call it the impedance. Okay. Now, in a purely inductive circuit, the impedance is the reactance. The impedance is the reactance. Later, when we add a resistor to the circuit, the impedance will be the sum of the reactance and the resistance. Right. So here the resistance is 0. So the current in the circuit will be the voltage divided by the reactance. Now, I know the voltage already, it's 10 volts at 0 degrees, and I want that to be in an RMS value. But what about the reactance? What is the reactance? Well, the reactance is equal to 2 times pi times the frequency times the inductance of the inductor. And so the inductive reactance will be 2 pi times the frequency of the circuit, which is 1 kilohertz, times the inductance of the circuit, which I said is 10 millihenries. And so when we multiply this out, we will get the value of the inductive reactance. And so we have 2 times pi times 1 kilohertz, which is 1,000, times 10 millihenries, which is 0.01. And we are going to get an inductive reactance of 62.832. 62.832. And that's going to be in ohms. The reactance is sort of like resistance. It's not resistance. It's opposition to change in current. But it causes the current to be less because the current can't change as rapidly. And so the overall RMS value of the current in the circuit is going to be less due to this reactance. And so we measure that in ohms. Right? It's very similar to resistance. Now, the inductive reactance is a vector. The inductive reactance will always be at positive 90 degrees. You don't even have to think about it. It's always going to be at positive 90 degrees. Well, why? Let's find out. Because the current is equal to the voltage over the reactance. Voltage is 10 volts at 0 degrees. And the inductive reactance is 62.832 ohms at 90 degrees. And so the question was why is it always at positive 90 degrees? So let's see, let's divide these two vectors. We divide the magnitudes first. 10 divided by 62.832, which is going to be 159.2 milli, that'll be amps, 159.2 milliamps. And the angle, we subtract the angles when we divide vectors, so 0 minus 90 is going to be negative 90 degrees. And if you remember, in an inductive circuit, we said that the current will always trail the voltage by 90 degrees. So the angle in this voltage is just a reference, right? The voltage is always considered to be at 0 degrees. we're saying that the current is going to be 90 degrees behind that 0 degrees, right? So it's 90 degrees behind. If the inductive reactance were not at an angle of positive 90 degrees, we would not have gotten an angle at negative 90 degrees. And so we saw an example earlier where we found the impedance by dividing the voltage by the current. The current was always negative 90 degrees. 0 minus negative 90 gave us positive 90. The inductive reactance will always be at positive 90 degrees. Okay? And the current in a purely inductive circuit will always be at negative 90 degrees. So let's look at a circuit now that has a resistor and an inductor. And so first let me start by saying that we've seen this already in a previous chapter. If an AC circuit only had a resistor, we would see voltage and we would see current, and they would be in phase. And so if the voltage we said was at 0 degrees, the current would also be at 0 degrees because there's no phase difference, and therefore the resistance would also be at 0 degrees because again there is no phase difference. And so when I say that the resistance in the circuit is 1 kilo ohm, that is also a vector, and it's at 0 degrees. It'll be the same as whatever the voltage is. The resistance does not offer resistance to change in current. The resistance does not cause the current to be out of phase with the voltage. So the resistance will always be at 0 degrees just like the voltage. Okay? But X sub L, on the other hand, as we saw before, will be at positive 90 degrees. And so again, the formula for X sub L is 2 times pi times F times L. So we'll have 2 times pi times the frequency of this circuit is 5 kilohertz times the inductance, which is 50 millihenries. So we have to start by solving any AC circuit by first finding the inductive reactance. The inductance itself doesn't tell us a whole lot about the effects that the inductor has on the circuit. Not until we find X sub L do we find that out. And so X sub L will be 2 pi times 5 kilohertz, so I'll do 5 EE3, times 50 millihenries, so 5 EE negative 3. And we get an inductive reactance of 1.571, and that'll be kilo. Inductive reactance is measured in ohms, and the phase angle of inductive reactance is always positive 90 degrees. Okay? And so the resistance is 1 kilo ohm at 0 degrees. The inductive reactance is 1.571 kilo ohms at 90 degrees. Now we have the information that we need to solve the circuit the same way we do any other DC circuit. We're going to follow the same types of steps. Our first goal is to find the total resistance. Now in an AC circuit we call that the impedance. The impedance is the combination of inductive reactance and resistance. And I'm adding them because they're in series. Okay, just like any DC circuit, right? So total resistance is going to be the sum of X sub L and R because they're in series. If they were in parallel, we would use the same kind of parallel formula, product over sum, something like that, or the reciprocal of the sum of the reciprocals. So the total impedance of this circuit will be X sub L, which is 1.571 kilo ohms at an angle of 90 degrees, and we're going to be adding to that 1 kilo ohm at 0 degrees, which is the resistance. Now when I'm adding vectors, it's going to be a lot easier for us if these vectors were in rectangular form. Right? It's a lot easier to add vectors in rectangular form than it is to add them in polar form. So the total impedance of the circuit is, I need this to be in rectangular form first. The x component is always going to be the magnitude times the cosine of the angle. Right? So the x component is 1.571 kilo ohms times the cosine of 90 degrees. The y component is going to be the magnitude times the sine of the angle. So it would be 1.571 kilo ohms times the sine of 90 degrees. And that'll be the j component of this vector. And then we're adding to this. We're going to be adding the resistance. And same thing, magnitude times the cosine of the angle. So 1 kilo ohm times the cosine of 0 degrees plus magnitude 1 kilo ohm times the sine of 0 degrees. And again, this will be the J component. And so I can type this into a calculator and I can figure out what these values are going to be. Okay, and so I'll go ahead and do that. So I have 1.571 EE3 for kilo times the cosine of 90 degrees, and we get 0. The cosine of 90 degrees is 0, and so we're always going to get 0 when we multiply by the cosine of 90. So the x component of the inductive reactance is 0, and the y component is going to be 1.571 EE3 for kilo times the sine of 90 degrees, and I get 1.571 kilo, and that's because the sine of 90 degrees is 1, and so we're just multiplying by 1 here. And so the x component will be, or I'm sorry, the y component is going to be plus 1.571 kilo ohms, and again that is the J component of that vector. And now we're adding in the resistance, and so again we'll have 1 kilo ohm times the cosine of 0, 1 EE3 times the cosine of 0, which is 1 E3, right, which is 1 kilo ohm, and that is because the cosine of 0 is 1, and so we're just multiplying by the cosine of 0 here. So the x component is 1 kilo ohm plus 1 kilo ohm times the sine of 0, so we have 1 E3 times the sine of 0, which is 0, because the sine of 0 is 0. So here we're multiplying by 0. So here we have 0J. And so this makes a lot of sense, because if you were to look at these two vectors, we have 1.571 kilo ohms at 90 degrees, and we have 1 kilo ohm at 0 degrees. Well, the x component of this vector is 1, and there's no y component because it's straight to the right. The y component of this vector is 1.571 because it's all straight up and there's no x component. And so when we have vectors at 0 and 90 degrees, the vector that is at 0 degrees is all in the x, right? It's all in the x. The vector that is at 90 degrees is all in the y. Okay, and so with a little bit of practice you'll get more familiar with that. It'll be a lot easier. And so when I add these two vectors together, I'm adding the x components together, 0 plus 1 kilo ohm, which is 1 kilo ohm. Okay, and then I add the y components together, 1.571 kilo ohms J plus 0 J. And so that's just going to be 1.571 kilo ohms J. And so this is the vector that represents the impedance. It was the sum of these two vectors. When we add vectors graphically, we know that the sum of the two vectors using the parallelogram method gives us some result like this. We're looking for this vector here, and it has an x component of 1 and a y component of 1.571 kilo ohms. And so this is the impedance. It's in rectangular form. I really need this to be back in polar form. And so to find the magnitude in polar form, we're going to take the square root of x squared plus y squared. So that's going to be 1 kilo ohm squared plus 1.571 kilo ohms squared. That'll be the magnitude. The angle will always be the inverse tangent of the y component, which is 1.571 kilo ohms, divided by 1 kilo ohm, the x component, right? Y divided by x. So it's always inverse tangent of y over x. So the x is 1 kilo ohm. Now when I divide these, the units cancel. Kilo ohms cancels out, right? So I didn't really need to write that there, but I did anyway. And so let's find the magnitude. We're taking the square root of 1 EE3 squared plus 1.571 EE3 for kilo squared, and we get 1.862. The impedance is 1.862, that's kiloohms, at an angle, and the angle will be the inverse tangent of 1.571 divided by 1. Again, the kiloohms canceled. Alright, I didn't have to do EE3. That part cancels out. We get 57.52 degrees. 57.52 degrees. And so, when you look at the sum graphically, we expect this line to be longer than the longer of the two components, which it is. We had 1.862. That was greater than 1.571. Right, so it's the magnitude is greater than either of the components, and the angle is a positive 57.52 degrees, which is about what my picture here looks like. Important thing is that it's in the right quadrant, and we can see that that's about what it should be. So we found the impedance. So we found the total impedance, 1.862 kiloohms at 57.52 degrees. I've written that here. And just like with a DC circuit, that's similar to the total resistance. That was the first step. The next step now is going to be to find total current. Total current is going to be the source voltage divided by the impedance, which in this case is like the total resistance. So we are going to have 10 volts at 0 degrees divided by our total impedance, 1.862 kiloohms at an angle of 57.52 degrees. Okay. So our total current will be, again, we're dividing vectors, so we're going to divide the magnitudes only. 10 divided by 1.862 kilo, and we get 5.371. 5.371, that's milliamps. And the angles, we subtract them, so 0 minus 57.52 is going to be negative 57.52. And what we see here is that in the inductive circuit, even though we also have a resistor in the circuit, Eli, that the voltage is going to be leading the current. The current is going to have a negative angle. Now, we've added the resistor in the circuit. It no longer is trailing by 90 degrees, but it's still trailing. And the reason the angle came out different is because we've added a resistor to the circuit. And that's what gave us a different angle here. So now we know the total current. And the current in the circuit is the same everywhere because it's a series circuit. This is RMS value. So the current is the same everywhere. We're going to have 5.371 milliamps at an angle of negative 57.52 degrees. That's for the resistor and the inductor. 5.371 milliamps at an angle of negative 57.52 degrees. And so now, just like in a DC circuit, we know the resistance of the resistor and we know the current in the resistor. We can find the voltage drop here. So the voltage drop across resistor 1 will be equal to R1 times the current in R1, which is going to be 1 kiloohm at 0 degrees. Remember, these are vectors. Always include the angle with your vectors. Times the current, 5.371 milliamps at an angle of negative 57.52 degrees. Okay, and so the voltage drop on the resistor will be, we have 1 kiloohm times 5.371 milli. The voltage drop will be 5.371 volts. And so remember, when we multiply vectors, it's okay that they're in polar form. That's actually what we prefer. We multiply the magnitudes together and then we add the angles. And so 0 plus a negative 57.52 is going to be negative 57.52 degrees. This is the voltage drop on resistor 1. And so what this means is that we see a total voltage that has an RMS value of 10. So the peak value is more than that, is 14.14. But the RMS value is 10 volts. And the voltage drop on R1 is going to be 5.371 volts, but it's going to be lagging by 57 degrees. And so remember, this is 360 total degrees, this is 180, 90 is right here somewhere, 57.52 is about right here somewhere. And so what we're going to see is the voltage drop on the resistor is going to be out of phase with the voltage drop, of the source voltage. The voltage drop on the resistor is out of phase by 57.52 degrees. It's out of phase by that amount with the source voltage. Now what about the voltage drop on the inductor? Well, we have a resistance value or a reactance value. We have 1.571 kiloohms at 90 degrees. That is the resistance, and we're multiplying by the current, which is 5.371 milliamps at an angle of negative 57.52 degrees. And so VL1 will be, again, we're going to multiply the magnitudes. So we have 1.571 EE3 for kilo, and we're multiplying by 5.371 EE negative 3 for milli, and we get 8.43, maybe 8.44 or so. Well, how about 8.438? 8.438 volts. Alright, so we multiplied the magnitudes. Now we will add the angles. And so I'll go ahead and do that. We're taking 90 degrees, and since we're multiplying, we're adding, and we're adding in a negative 57.52. And so we get an angle of 32 degrees, 0.48. 32.48 degrees. Now, what does that mean? That means that the voltage drop on the inductor is actually leading the voltage drop of the source voltage. Right? So the resistor's voltage drop was lagging the source voltage, but the voltage drop in the inductor is leading. It's very interesting. And so the voltage drop on the inductor is looking something like this, where it's to the left, it's leading the source voltage. Okay, very interesting. We can see this in the lab. We'll view these waveforms on an oscilloscope, and we'll see that they're out of phase in this manner. Now we know the voltage drop on the resistor is 5.371 volts at an angle of negative 57.52 degrees. And the voltage drop on the inductor is 8.438 volts at an angle of 32.48 degrees. Now we can check these answers the same way we did in a DC circuit. In a DC circuit, we use Kirchhoff's voltage law, which says that the source voltage has to be equal to the voltage drop on one of the components plus the voltage drop on the other components, right? The sum of the voltage drops in the circuit have to add up to the source voltage. And so let's see if that's true. We're saying that 10 volts at 0 degrees, which is the source voltage, must be equal to the voltage drop on the resistor, 5.371 volts at an angle of negative 57.52 degrees. And we'll be adding to that the voltage drop on the inductor, which is 8.438 volts at an angle of 32.48 degrees. And so we want to add these vectors. They're in polar form. We need them to be in rectangular form for us to add them. And so the resistor's voltage drop is 5.371 volts at negative 57.52 degrees. To change this to xy components, we take the magnitude times the cosine of the angle, gives us x component. Magnitude times sine of the angle gives us the y component. And so we will take 5.371 volts times the cosine of negative 57.52 degrees, that is the x component, plus 5.371 volts times the sine of negative 57.52 degrees, that'll be the j component or the y component. Right, so that's all one vector. That's the xy representation of the first vector. And then we're adding to that the second vector, which is the inductor's voltage drop, 8.438 volts times the cosine of 32.48 degrees, plus the y component, which will be 8.438 volts times the sine of 32.48 degrees. And that'll be the J component, the Y component. So let's calculate this out. We will find the X and Y components. Okay, so we think that 10 volts, we start over here. We think that 10 volts at 0 degrees should be equal to the sum of these two. So I have 8.438 volts times the cosine of 32.48 degrees. So the X component of this vector, oh, I'm sorry, I did that wrong. Let me start up here. We have 5.371 times the cosine of negative 57.52 degrees. The X component of this vector is 2.884 volts. The Y component will be 5.371 times the sine of negative 57.52 degrees, and we get negative. So normally when I write my rectangular vectors, I usually write plus. That's because the Y component has been positive. Here the Y component though is negative, and so I'm going to make sure I write minus here. The Y component is going to be negative 4.531 volts, and that's the J component of that vector. And then we're going to be adding to this other vector, the second vector here. And so we have the 8.438 times the cosine of 32.48 degrees. The X component of this vector is 7.118 volts. And then the Y component is 8.438 times the sine of 32.48 degrees. And we get a positive 4.531 volts J. And so we think that when we add these together, we should get 10 volts at 0 degrees. And so when we add these together, we add the X components together, we add the Y components together. And so I have a positive 2.884, and I'm adding to that 7.118, and we get 10.002 volts. That's just a little bit of rounding error. For the Y components, we have a negative 4.531, and we're adding to this a positive, adding a positive 4.531, and no surprise, we get 0 plus 0J. And so 10 volts at 0 degrees, we think that's equal to 10.002 volts plus 0J, right? So this is the polar form, this is the rectangular form. If you square both of these and add them together, that will give you the magnitude. And if you take the inverse tangent of y divided by x, that will give you the angle. And so we'll go ahead and do that. Is 10 volts at 0 degrees equal to this form of the rectangular form of the vector? It is. You can probably see that already, but I'll go ahead and do it anyway. We're going to take the square root of 10.002 volts squared plus 0 volts squared. Alright, so square them both, add them together, and take the square root. That gives you the magnitude. The angle will be the inverse tangent of the y component, which is 0, divided by 10.002. And again, these are both in volts, right? This is 0 volts. And so the volts cancel. And so 10 volts at 0 degrees is this equal. So we take the square root of 10.002 squared plus 0 squared, and so we get 10.002, which is pretty close to 10. That's rounding error. Volts, that is the magnitude of the vector. The angle will be the inverse tangent of 0 divided by 10.002. Of course, 0 divided by any number is 0. So the inverse tangent of 0 is 0 degrees. And we can see that these are equal. So Kirchhoff's law holds true. If we have two components in series in a circuit, their voltage drops should add up to the source voltage, and they do. And so that's how we know we've got the right answers here. Let's look at the power for this circuit. Recall that the power is the voltage times the current. And so if if we look at the voltage and current waveforms, we have the voltage, something like this, and we have the current lagging by 57 degrees, so something like this. And if you look at the voltage and the current at various points in time, let's look at this point first. At this point in time, the current is 0, but the voltage is a positive value. If the current is 0, the power at that point in time must be 0. And if we look at this point in time, here the voltage is 0 and the current is some positive value. Again, the power must be 0 if the voltage is 0. But between these 2 points in time, the voltage and the current are both positive values. So here the power will be a positive value. At this point in time, the current is 0 again, and the voltage this time is negative. And so at this point in time, the power will be 0 because the current is 0. But between these 2 points in time, we have the current being a positive value and the voltage being a negative value. And so if we multiply these together, between this time interval, we expect the power to be a negative value. And again, from here to here, the voltage and current are both negative values. And these waveforms continue on, of course. And so from this point on until this point, you can see again that the current is negative, the voltage is positive, we expect a negative value. And so the point is that sometimes the voltage is positive, sometimes it's negative, and sometimes it's 0. And so that presents a bit of a problem for us. So let's look at the vectors. We have the voltage, which is 10 volts at 0 degrees. And we have the current, which is 5.371 milliamps at negative 57.52 degrees. And so there's a phase angle between the two. There's a difference in angle of 57.52 degrees. And so if we look at just the current vector, and again it's 5.371 milliamps at negative 57.52 degrees, the current vector has two components. If we look at the vector in xy form, we have an x component and we have a y component. The x component is positive in this example, and the y component is negative. The x component of the current vector is in phase with the voltage. The y component of the current is perfectly perpendicular to the voltage. And so let's resolve this vector into its two components. We can find the x component of the vector by taking the magnitude multiplied by the cosine of the angle. So 5.371 milliamps times the cosine of negative 57.52. And so the x component of this vector is 2.884 milliamps. And this component is at 0 degrees. And the y component is 5.371 milliamps times the sine of negative 57.52 degrees. And we see that the y component is negative 4.531 milliamps, and the y component is at negative 90 degrees. So when we go to calculate the power, we only want to consider the part of the current vector that is perfectly in phase with the voltage. If we multiply this vector at 0 degrees, this component of the current vector at 0 degrees, times the voltage, which is at 0 degrees, we get what was called the true power. And if we were to multiply the y component of this vector times the voltage vector, and they're 90 degrees out of phase, we'll get what we call volt-amps reactive, or VAR, or VARs. And that represents the imaginary component of the power. And so what's happening here is the voltage is negative, but the current is still positive. That's because the magnetic field around the inductor is collapsing, and it's keeping the current flowing in the original direction even though the voltage has reversed polarity. And so here the current being supplied to the circuit is the energy being given up by the collapsing magnetic field. And so that was energy that was previously stored. So we consider that the imaginary component of the power. And if we take the original vector with its angle and we multiply it just by the voltage, we get something that we call volt amps. Right, so you simply take the voltage and multiply by the current, we get what is called the volt amps. So using our new definition, we can find the volt amps by taking the voltage and multiplying by the current without regard for any of the phase angle. So the volt amps for this circuit will be equal to the voltage, which is 10 volts. Notice I'm still using RMS values, multiplied by the current, which is 5.371 milliamps. And again, I'm not considering any part of the phase angle for these vectors. And so if we take 10 volts and we multiply by 5.371 milliamps, we're going to get 53.7. The volt amps is 53.71, and we call this millivolt amps. Right? This is not in watts because the voltage and the current are not in phase with one another. So we call this volt amps. We can find the true power by multiplying the voltage times the x component of the current. And remember, the x component of the current was multiplied by cosine theta. If we multiply cosine theta by the magnitude of the current, we get the x component of that vector. Right? So the x component of the current vector, which we just looked at, that's what we're interested in here. So the true power, the actual power measured in watts, is going to be the voltage, which is 10 volts. We're going to multiply by the current, which is 5.371 milliamps. So far no different than what we've done before. But we're also going to multiply by the cosine of the angle between the two vectors. The voltage is at 0 degrees, the current is at negative 57.52. The angle between them is 57.52. Notice I'm using the absolute value of the angle here. I'm looking for the difference between the two angles. So 0 minus a negative 57.52 is positive 57.52. We're interested in the absolute value of the angle here. So the power will be, well, 10 volts times 5.371 milliamps is 53.71 millivolt amps. And now if I multiply by the cosine of 57.52 degrees, we will get the true power measured in watts. So we'll have 53.71 milli, and we're going to multiply by the cosine of 57.52 degrees. And so the power of this circuit is 28.84 milliwatts. This is true power measured in watts. Now we can also find the VARs, or VAR, volt amps reactive. This is going to be the voltage times the current times the sine of the angle. So here we're looking at the y component of the current vector. So VAR will be, well, voltage times current, no different than what we did before, 53.71 millivolt amps. And if we multiply by the sine of 57.52 degrees, we will get the VARs. And so we have 53.71 millivolt amps times the sine of 57.52 degrees, and we get VAR is equal to 45.31 millivar. Okay, and so again, if we look at these vectors, the true power is the actual wattage of the circuit. We have 28.84 milliwatts. And the volt amps is going to be the hypotenuse of this triangle, 53.71 millivolt amps. And the VAR is the other leg of the triangle, 45.31 millivar. And the angle in this right triangle that we've just formed is going to be that 57.52 degrees. So this right triangle represents the power dissipation of the circuit. We have the true power measured in milliwatts. This was the voltage times the in-phase part of the current. We have the VARs, which is the imaginary power. This is the component of the current that is perpendicular to the voltage. Okay, so measured in volt amps reactive. And then we have volt amps, which is the hypotenuse of the triangle. That was strictly the voltage times the current without any regard to the angle. And so this is the true power dissipated by the circuit. For an equivalent DC circuit, it would be dissipating 28.84 milliwatts. The VARs is a part of the circuit that accounts for energy being stored in the inductor and then given back to the circuit later. The hypotenuse is simply the voltage times the current without any regard for the angle. Let's record these three values over here by the source. The true power was 28.84 milliwatts. The VARs was 45.31 millivar. And the volt amps is 53.71 millivolt amps. So those are the three components of the power associated with this circuit. Now let's look at the power associated with just the resistor. Notice that the voltage and the current on the resistor are in phase, and that's not by coincidence. The phase angle of the resistance is in phase with the voltage. The resistance has no phase angle. It's always whatever the angle of the voltage is at any point in time. And so they're in phase. And so here the power dissipated by R1 is simply the voltage times the current. The power for R1, and again that's because they're in phase. The power used by resistor 1 is going to be 5.371 volts. Times the current, which is 5.371 milliamps. And if I wanted to be very technical, I could say times the cosine of the angle. That was our formula for power for the whole circuit. But remember that the angle here means the difference between the two angles. And so a negative 57.52 minus a negative 57.52 is 0. And the cosine of 0 is going to be 1. So this term will cancel out. So the true power used by the resistor will be 5.371 volts times 5.371 milliamps. The true power will be 28.85 milliwatts. Now, we could also look at the volt amps for the circuit, for the resistor. The volt amps for the resistor is just voltage times current without regard for the angle, and so we're going to get the exact same answer. The volt amps is 28.85 volt amps. We could also look at the VAR for the resistor, which is going to be voltage times current times the sine of the angle. And here, I'll go ahead and write this out. The voltage is 5.371 volts. Current is 5.371 milliamps times the sine of the difference between the angles, which is 0. Right, so again, the difference between these two angles is 0. There's no phase angle between them. The sine of 0 is 0, and 0 times any number is 0. So the VAR for the resistor is 0. And so notice what happens with resistors. All of the power is true power. Right, so the volt amps, I should say that all of the volt amps is actually true power and none of it is VAR. That's what we get for the resistor. So for the resistor, the power is 28.85 milliwatts. Okay, and there is no VAR, and all of the volt amps is watts. Now let's look at the power dissipation for the inductor. Let's start by finding the volt amps. The volt amps of the inductor is simply the voltage times the current. And so the volt amps will be the voltage, which is 8.438, times the current, which is 5.371 milliamps. And again, for volt amps, we don't consider any part of the phase angle. And so the volt amps will be 8.438 volts times 5.371 milliamps. The volt amps for the inductor is 45.32 millivolt amps. Now let's look at the true power for the inductor. True power will be voltage times current times the cosine of the angle between them, between these two angles. And so the power will be the voltage times the current, which is going to be the same value we had here, 45.32 millivolt amps, times the cosine of the angle between them. And so if you look at the two vectors, we have a voltage that is at positive 32.48 degrees. And if you look at the current, we have a current that is at an angle of negative 57.52 degrees. And the difference between these two angles is 90 degrees. And that's not coincidence, that's always going to be the way that it works. The voltage and the current for the inductor are always going to be 90 degrees out of phase. We saw that in the purely inductive circuit that didn't have a resistor. The voltage and the current on the inductor, when there was no resistor, were 90 degrees out of phase, and that's going to be the same whether we have a resistor or not. And so the angle here is 90 degrees. And so the power will be, well, the cosine of 90 degrees, let's take a look, the cosine of 90 degrees is 0. And so cosine of 90 is 0. 0 times any number is 0. There's 0 watts being consumed by the inductor. And that's because the inductor does not have any resistance. In order for there to be power consumption, we must have resistance. And so the inductor does not actually consume any power, theoretically. The inductor does actually have some resistance. The copper that makes up the windings does have some resistance. We'll talk about that in just a second. So the power consumed, theoretically, by the inductor in the circuit is 0 watts. That's because any energy that the inductor uses to grow its magnetic field is later returned back to the circuit when that magnetic field collapses. And so the inductor does not actually consume any power. It consumes some energy, but then it gives that energy back to the circuit for a net of 0 watts. Now if we look at the var, we will have the voltage times the current times the sine of the angle. Again, the voltage times the current will be 45.32 millivolt amps. We're going to be multiplying by the sine of the angle, which is 90 degrees. The sine of 90 is 1, and so when we multiply 1 times any number, we just get that number. We will have 45.32 millivar. And so let's look at the three components that make up this this triangle here. We have the power, which is on the x-axis, which is 0, so there's no x and y. There's no x component to this vector. We have the var, which is the y component, and so that will be 45.32 var. And the volt amps and the var is equal because this isn't actually a triangle at all, it's just a single vector. Right? So there's no x component here. The hypotenuse and one of the legs of the triangle are equal. The other leg of the triangle is 0. So that means that the inductor only has var. All of the volt amps is contributed to volt amps reactive. And so I'll record this here as 45.32 millivar. So in DC circuits, we said that the sum of the power consumptions of all of the components in the circuit should add up to the power consumption, the total for the circuit. And you can see that all of the var for the total of the circuit comes from the inductor. All of the true power comes from the resistor. And so what that means is we have a vector triangle that shows true power, which comes from the resistor, which is 28.85 milliwatts. We have a var component, which all comes from the inductor, so 45.32 millibar, and this vector triangle has a hypotenuse, and the hypotenuse, it turns out, is the volt amps of the total circuit, so 53.71 millivolt amps. So the var is the y component, the true power is the x component, and the volt amps is the hypotenuse. And so for any right triangle, we can say that the hypotenuse should be equal to the square root of the sum of the square of the two legs. So the square root of 28.85 milliwatts squared plus 45.32 millibar squared. This is how we can check our answer. We're actually adding these two vectors together. If you resolve this vector at 0 degrees into xy components, you'll only get an x component. If you resolve this vector into xy components, you'll only get a y component. And so when we add them together, we get this vector that has this x and y component. And so this is the x and y component of the resultant, at least we think. We're checking that, and we're going to resolve that back into a polar form. So we think that 53.71 millivolt amps should be equal to the square root of the sum of these squares. And so let's take a look here. We have 28 point, actually let me start over. Let's say the square root of 28.85. Let me get a parenthesis in there. 28.85 milli, that's squared, plus 45.32, and that's milli as well, squared, and oops, made a mistake somewhere here. Let's see. Let's start over. Square root of parentheses 28.85 milli squared plus 45.32 milli squared, and we get 53.72 milli volt amps. And you can see there's a slight rounding error here, but this shows us that we've got the correct answers. We have one more idea to discuss before we conclude this circuit. I'm just going to redraw the circuit. We have a circuit with a resistor and an inductor, but the inductor technically does have resistance, right? The copper wire that makes up the inductor does have some resistance. And so the inductor itself can be thought of as a resistor and an inductor. So this resistance and inductance represents the inductor in the circuit. There is some resistance here. It's small. It's very small. For example, maybe it's 10 ohms. It's only 10 ohms. Okay, and so we have 1 kilo ohm resistance at 0 degrees. Resistance is always at 0 degrees, and the inductance is 50 millihenries. Right. So it's the same circuit, but now we're considering the actual resistance of the inductor, and we still have a 10 volt source here at 0 degrees at 5 kilohertz. And so the inductor has what we call a Q rating, which stands for quality. The quality of the inductor is described as the inductive reactance divided by the resistance. So for this example, Q will be the inductive reactance, which again is 2 times pi times the frequency times the inductance, right? That's X sub L, divided by the resistance of the inductor. Okay, and so the quality of this inductor is 2 pi FL, which we've already calculated, is 1.571 kilo ohms. The resistance of the inductor is 10 ohms. And so if we divide these, that will give us a rating of quality for this inductor. So we have 1.571 kilo ohms, and we're dividing by 10 ohms. And so the quality of this inductor is 157.1. That's a unitless number. The ohms cancel. And so the higher the quality, the better the inductor is in the circuit. Notice that the quality depends on the frequency, right? The X sub L value came from the frequency of the circuit. So if the frequency of the circuit was less, the quality of the inductor actually goes down, right? Higher frequencies result in higher qualities of inductors in the circuit. And so what we're saying is that if the frequency is higher, X sub L is larger, and we want X sub L to be much larger than the actual resistance of the circuit. And so if you looked at the vectors that make up the total resistance of this circuit, we have the inductive reactance, the inductive reactance, X sub L. We have the resistance of the circuit, right, which is the actual resistor. And then we also have the resistance of the inductor, which is relatively small, right? We want it to be relatively small. And so the total impedance, Z, the resultant of these three vectors, is going to account for R sub L. And so we want the quality to be as high as possible. The higher the quality, essentially the smaller this R sub L value is compared to this X sub L. So higher quality results in smaller changes in Z. A low quality would have a much larger resistance, which is going to cause the phase angle for Z to be reduced. Right? If this is longer, for example, if R sub L was big, our Z would be out here somewhere, and you can see that the phase angle would be smaller, and the value of Z, the magnitude of the vector would actually be longer. So higher Q's mean less of an effect of the resistance of the inductor. A small Q means a greater effect from the resistor of the inductor.